Good day, everyone. This is Dr. Soper here, and today we will be discussing the fourth topic in our series of lectures on databases. And the topic today will be on data modeling and the entity relationship model, or ER model for short. We have many different objectives for our lecture today. Generally speaking, our goals are to understand the reasons why data models are valuable and to gain both understanding and expertise in reading and creating entity relationship or ER models. Along the way, we will explore the various elements of entity relationship models, and we will further discuss different types of relationships that can exist between entities, including unary or recursive relationships, binary relationships, ternary relationships. We will also learn about a concept known as a cardinality, which describes the number of instances of one entity that are allowed to participate in a relationship with another entity. And toward the end of our discussion, we will explore the differences between strong and weak entities, and we will look at the different types of weak entity relationships, including both identifying and non-identifying relationships. We will then conclude this lecture with a discussion of supertype and subtype relationships, and an examination of recursive relationships within the entity relationship model. To begin, let's take a broad view and consider the three different stages of database development. The first stage, prior to actually developing a database itself, is to perform what we call requirements analysis. This is the process of gathering information so that we can understand the data problem for which we are attempting to design a solution. Once we have completed requirements gathering, we can then move into the design phase. And the design phase is where we will create data models, which are graphical representations of the database solution which we ultimately hope to implement. Finally, the third stage of database development is actually implementing our database designs as a real-world functioning physical database that can actually be used by an organization to solve one or more data problems. Broadly speaking, the requirements analysis stage is about gaining an understanding of the data problem for which we are trying to design a solution. And for this purpose, we have many different possible sources of information. They can include interviews with users, existing forms, reports, or queries. So these might be forms, reports, or queries that are used with a current system. If the organization is going through a broader systems design process, then use cases from within the unified modeling language may be available to us. We may also consider business rules and observation, where we simply observe the way that various employees do their jobs in an effort to understand their data needs. And of course, we may use JAD sessions. These are joint application development sessions, which are characterized by assembling all of the stakeholders in a project together in a single room. So you may have systems designers, database designers, users, executives, potential customers, etc. And everyone in the room simply has a discussion about what they want the proposed new system to do and how they want that system to function. sort of information gathered from these joint application development sessions can then be very useful for developing a system in general, and specifically in our case, for developing the database to support that system. After we have completed requirements analysis, what we learn from that requirements analysis process then becomes our data model. So we take everything that we learn through the requirements analysis stage and we process and distill all of that information into a data model, where a data model is a graphical representation of the database system that we ultimately hope to implement. The most popular type of data model that is used in the database world today is known as an entity relationship, or ER, data model. These ER models consist of three major graphical components. They are entities, which we have spoken about previously as tables or relations, attributes, for which several different types might exist, including identifiers or keys, and non-key attributes, and our third and final component are relationships. These are relationships between entities. Before we proceed, I need to speak briefly about the distinction between an entity class and an entity instance. An entity class can be thought of as a structural description for the individual occurrences of an entity. I know that description contains a lot of technical jargon, so perhaps a better way of understanding this concept is to link it to other concepts which serve a similar purpose. Examples might be a recipe or blueprints that are used by an architect. In the first case, let's consider a recipe for baking a cake. If this is a generic recipe, we might have some basic instructions, mixing flour together with sugar and eggs and baking powder. Put that in an oven. We cook or bake our cake, and then we add whatever sort of frosting we like. So the recipe gives us a basic framework or guideline on how to produce a cake, but ultimately the cake that is created is a unique individual item. In our analogy, the recipe is equivalent to an entity class, while the resulting specific individual real-world cake is equivalent to an instance of the entity. Similarly, we might consider architectural blueprints, where we may have a generic set of blueprints that tell us how to design a basic house, but then the homeowner who is building the house may be able to make some specific decisions, such as what type of appliances they want in the kitchen, or what color they want the paint to be, or what type of carpeting they want. All of those individual characteristics make that the resulting real-world house a unique, specific item. In our analogy, the architectural blueprints are similar to an entity class, while the resulting individual real-world houses that are created as the result of following those blueprints would be instances of the entity class. So just remember that an entity instance is an occurrence of an entity class. If we have an employee entity, that is, an employee entity class, we may define attributes that we want to track for all employees, such as an employee ID number, an employee name, an employee department. When we add a new row of data to that table and we specify specific values for those attributes, perhaps employee ID number 1 named Dan, who works in the marketing department. We are describing a real-world entity. That new row of data is an instance of an employee. And as far as the database is concerned, that row of data is an employee. Here we see some additional examples. Our entity class in this case is an item, and we can see that the item entity contains 5 attributes: item number, description, cost, list price, and quantity on hand. And then we see 2 instances of that entity. So the instances of the entity represent an instantiation of the entity class. This idea, if you've had some object-oriented programming, is directly analogous to the concepts of a class and an object in the object-oriented programming paradigm. Next, I would like to talk about attributes. An attribute is a specific piece of information that we would like to keep track of for each instance of an entity. If we're talking about an employee, we may have attributes that we want to track, such as the employee's name, or their age, or the date when they were hired, and so forth. If we're talking about a project entity, we may have attributes that we want to track, such as a project name, or the start date of the project, or the type of project, or a description of the project. The point here is that as we fill in values for these individual attributes, what we are really doing is defining a specific instance of the entity class. So we are defining an employee, or we are defining a real-world project by providing values for these attributes. Each attribute that is part of an entity has a data type as well as several other properties. So we may define an employee ID number, for example, as an integer. We may define the employee's name as a varchar with a maximum length of 50 characters. We can also specify additional properties for each attribute, such as whether or not the attribute is allowed to store null values, or perhaps we want to provide a textual description of the attribute. So in addition to a data type, an attribute can have other properties as well. Broadly speaking, we can consider 2 different types of attributes. There are, first, identifiers, which we will generally refer to as keys, and then we have non-key attributes. In the first case, identifiers are attributes whose values are used to identify an instance of the entity class. Common examples of identifiers or keys might be a social security number, a student ID, an employee ID, an email address, or even a department ID. One of the important things to remember about keys is that they can either be unique or non-unique. If a key is unique, that means that each instance of the entity, or if you prefer to think about it as each row in the table, will have a unique value for that attribute. For example, our employees may have an employee number, and we would almost certainly want each employee to have a unique employee number so that we can keep track of our employees individually by using that number. By contrast, we can also have non-unique keys, and non-unique keys are used in order to group instances of an entity class into categories. An example might be a department ID. more than one employee can have the same department ID. And what that tells us is that the employees which share the same department ID all belong to or work in or are affiliated with the same department. In that case, the key would be non-unique because more than one instance of the employee class can have the same department ID. Recall also that we have composite keys, and that a composite key gains its uniqueness by combining the values of two or more attributes together. The example that we used previously in this series of lectures was the flight number and the date of a flight. So we may have, for example, United Airlines Flight 33 that takes place on the 17th of March, 2016. There may be several other flights that take place on the 17th of March, and we may operate Flight 33 every day, but if we combine those values together, we can then use Flight 33 on the 17th of March to identify a specific real-world flight with a real airplane, real passengers, and so forth. The combination of those two values will be unique. Before we continue our exploration of entity relationship models, I think at this point it would be a good idea to provide examples of different ways in which entities might be represented in an entity relationship diagram. The simplest way of representing an entity is just to use a rectangle which contains the name of the entity. This is usually used for conceptual data modeling. I may, for example, have an item entity. All I need to know is that an item entity is related to other entities in some way. I don't yet care about the various attributes that will become a part of the item entity. Another way of graphically depicting these entities is to show the entity and just include its key attributes, attributes which are serving as identifiers or keys for the entity. We might, for example, have an item entity, and we may have defined an item ID as its primary key, and we will list just that single key attribute so that when we create relationships between the item entity and other entities, we can see which attributes are involved in the relationship. And that may be all of the information we need during a preliminary stage of data modeling. Finally, we have a way of representing an entity in its entirety, which includes not only the name of the entity and its key attributes, but also all of the other non-key attributes that together comprise the entity as well. Next, I would like to talk about relationships between entities. If you recall from some of our earlier lectures, we talked about how relationships naturally emerge among the various business concepts for which we might want to track or record information. A department, for example, can have many different employees, or a customer can place many different orders, or a product can have many different suppliers. These are all examples of relationships among entities, relationships among business concepts. From the perspective of entity relationship modeling, then, we can consider several different types of relationships. And these types of relationships can be defined by what we call the degree of the relationship, where the degree of the relationship refers to the number of entities that are participating in the relationship. Common examples include a unary relationship. This would be a degree 1 relationship in which an entity is related to itself. We would also call that a recursive relationship. We may also have a binary relationship, or a degree 2 relationship, where one entity is related to another entity. Binary relationships are by far the most common types of relationships in entity relationship modeling. We may also have a ternary relationship, or a degree 3 relationship. In a ternary relationship, we would have 3 entities involved in the relationship. So the degree then simply refers to the number of entities which participate in the relationship. Let's see some examples. Here we see a conceptual drawing of a unary relationship. Remember that a unary relationship is an entity that is related to itself. In this case, we have a person entity, and the person entity has a relationship to itself that we are calling marriage. What we can infer from this diagram then is that a person can be married to another person. The possibility exists for instances of the person entity to have this marriage relationship with each other. So a person can be married to another person. The person entity is related to itself in a unary relationship. Here we see an example of a binary relationship. In this case, we have 2 entities, employee and parking space, and these 2 entities are related to each other. So an employee may park in a parking space, or a parking space may be assigned to an employee. This is a binary relationship, or a degree 2 relationship, and these types of relationships are the most common in entity relationship modeling. Here we see a conceptual ternary relationship. Recall that in a ternary relationship, 3 different entities participate. In this case, we have a doctor entity, a patient entity, and a drug entity. The intersection of these 3 entities, then, is a prescription. So a doctor writes a prescription which involves a patient and a specific drug. These 3 entities together, conceptually, are involved in a ternary relationship. Next, let's expand the set of tools that we have available for describing the relationships between entities. We will begin by learning 2 simple symbols for describing conceptual relationships between entities. The first of these symbols is a simple line, and it is used to represent a conceptual 1 relationship between entities. The second of these symbols is known as a crow's foot because it is supposed to look like the foot of a bird, and we use this symbol to represent the conceptual notion of many. Let's see how these conceptual crow's foot relationship symbols might be implemented to describe relationships between entities with a little more detail. To begin, we can consider a conceptual 1-to-1 binary relationship. In a 1-to-1 relationship, an instance of one entity is related to one instance of another entity. Here we see an example of a 1-to-1 relationship between an employee entity and a locker entity. So we might imagine that an employee is assigned to exactly one locker, and a locker can be assigned to just one employee. This is a 1-to-1 relationship. Next, we can consider a 1-to-many relationship. I should note that 1-to-many relationships are by far the most common types of binary relationships in entity relationship modeling. In a one-to-many relationship, a single instance of one entity is conceptually related to many instances of another entity. A simple example of this type of relationship would be the one-to-many relationship which exists between a department and an employee entity. So an employee works in one department, but a department can have many employees. This is a one-to-many relationship between entities. Finally, we can have a conceptual many-to-many relationship. In a many-to-many relationship, many instances of one entity can be related to many instances of another entity. In this example, we see a conceptual many-to-many relationship between an item entity and a supplier entity. What we can infer from this diagram is that a supplier can supply many items, while a given item might be supplied by many different suppliers. An extremely important point to remember is that although we can think about these many-to-many relationships conceptually in this way, in a real-world implementation of a database, we cannot directly implement a many-to-many relationship between two entities. We must always have a third entity or a third table which will sit between them, which acts as a lookup table and provides us with the ability to actually link many instances of one entity with many instances of another. In this example, to actually implement the many-to-many relationship between our item and supplier entities, we would need to create a third entity to sit between them, which we might label item supplier, which we could use to actually link items and suppliers together. Now that we are able to better describe the relationships between our entities by using the concepts of one and many, we can talk about the notion of cardinalities, which allow us to be even more precise in describing and defining the relationships between entities. In entity relationship modeling, there are two different types of cardinalities. The first is a maximum cardinality, and the second is a minimum cardinality. The maximum and minimum cardinalities respectively allow us to specify the maximum number of instances of one entity that are allowed to participate in a relationship, and the minimum number of instances of an entity that must participate in a relationship. Maximum cardinalities are typically defined as one, many, or some other specific positive fixed number. By contrast, minimum cardinalities are typically specified as 0 or 1, where 0 would indicate an optional relationship, and 1, as the minimum cardinality, would indicate a mandatory relationship. Remember that a minimum cardinality refers to the minimum number of entity instances which must participate in the relationship. The relationship might be optional, or it might be mandatory, 0 or 1. Here we see how we can specify minimum and maximum cardinalities using our crow's foot symbols. To begin, consider a hash mark across the relationship line. You will notice that this hash mark looks similar to the number 1. And that's an easy way of remembering what the hash mark represents. It represents a cardinality of 1, and it can be used to represent either a minimum or a maximum cardinality. In our first example, we have what we would call a one and only one relationship. The minimum cardinality and the maximum cardinality are both specified by this hash mark across the relationship line. Remember that the symbol which appears closest to an entity is always the maximum cardinality, while the adjacent symbol is the minimum cardinality. Now that we know the meaning of this hash mark across the relationship line, we can understand the notion of a one-to-many relationship. In a one-to-many relationship, we are saying that many instances of one entity may participate in a relationship with a single instance of another entity, but at a bare minimum, at least one entity instance must be involved in the relationship. Again, remember that the symbol which appears closest to the entity is the maximum cardinality, while the adjacent symbol is the minimum cardinality. Next, let's consider the circle symbol. You will notice that this symbol closely resembles the number 0, and you can use that as a way of remembering its meaning. The circle symbol represents a minimum cardinality of 0. Note that the maximum cardinality can never be 0. If the maximum cardinality were ever 0, then a relationship could not actually exist between two entities. You would be saying that no instances of one entity are ever allowed to participate in the relationship. So the only time we will see this 0 or circle symbol is when it is being used to represent a minimum cardinality. Now that we're familiar with our three different types of cardinality symbols, that is, the hash mark across the relationship line, the crow's foot symbol, and the circle, we have everything that we need to describe the four different types of specific relationships which might exist among entities in an entity relationship model. They are one and only one, or if you prefer, exactly one, a one-to-many, a 0-to-1 relationship, in which the minimum cardinality is 0 and the maximum cardinality is 1, or we may have a 0-to-many relationship in which the minimum cardinality is 0 and the maximum cardinality is many. Let's see some examples of these fully specified cardinalities being used to describe relationships between entities. Here we see a binary relationship between a customer entity and an order entity. Note that relationships can be read in two different ways. In this example, as we follow the relationship line from customer to order, we would read the relationship as follows. A customer can place one to many orders. That is one way in which the relationship can be read. But note that we can also read the relationship moving in the opposite direction, in the direction from order to customer. When we read the relationship in that way, we would say an order can be placed by one and only one customer. The diagrams that we have been seeing on the previous slides are what are known as entity relationship diagrams. They are graphical ways of describing the relationships among the various entities that will eventually become a part of the database. In these entity relationship diagrams, our entities or our tables, if you will, are represented by rectangles. Inside of those rectangles, we will see the names of the entities and potentially the attributes that together define the entity. Entity relationship diagrams also depict relationships, and these are shown by using lines that interconnect our entities. And as we saw on the previous slide, the specific nature of those relationships is depicted using our cardinality symbols. Specifically, we use crow's foot symbols in order to provide specific details about the nature of the relationship between two entities. All of the examples that we've seen today can be thought of as what we would call has-a relationships. And this term is used because an entity has a relationship with some other entity. For example, an employee has a locker. A department has an employee. There are other types of relationships between entities which are called is-a relationships, and we will discuss these a little later. First, however, let's talk about strong and weak entities. To begin, a weak entity is an entity whose instances cannot exist in the database unless they are related to an instance in another entity. By contrast, a strong entity is an entity whose instances can exist independently. They do not rely on the existence of instances of any other entity in order to be able to exist. They can be added to the database independently. Consider, for example, the relationship between a customer entity and an order entity. New customers can be added to the database without any additional information being required to exist in any other entities. However, we cannot add an order to the database unless that order is associated with an existing customer. In this case, in this example, a customer would be a strong entity, whereas an order would be a weak entity. Beyond the distinction between strong and weak entities, we also need to note that there are two different types of weak entities. These are ID-dependent weak entities and non-ID dependent weak entities. To begin, an ID-dependent weak entity is a weak entity whose identifier, whose uniqueness, is partially linked to its parent entity. Another way of saying that is the ID-dependent weak entity will have as part of its primary key the primary key of its parent entity. In this way, the database will enforce the constraint that instances of the ID-dependent weak entity cannot exist without being associated with an instance of its parent entity. Here we see some examples of these ID-dependent weak entity relationships. In the first case, we may have a parent entity, which we will call building, and a child entity, which we will call apartment. In this model, an apartment cannot exist without belonging to a building, and this constraint is enforced by making the building name a component of the primary key for apartment. If the relationship between a strong entity and a weak entity is ID dependent, then we call that relationship an identifying relationship. And this can be seen graphically in entity relationship models by the use of a solid relationship line connecting the strong entity to the weak entity. So just to reiterate, ID-dependent weak entity relationships are known as identifying relationships. These are represented using a solid line on the entity relationship diagram. They are called identifying relationships because a part of the identifier of the weak entity is derived from the parent. If, by contrast, the identifier of a weak entity is not partially composed of the identifier of a strong entity, then we call that a non-identifying relationship, and we can say that the weak entity is non-ID dependent. In our entity relationship diagrams, these non-ID dependent relationships are represented with a dashed relationship line. And this dashed relationship line is also used to model relationships between strong entities. If the relationship between a strong entity and a weak entity is a non-ID dependent relationship, then the primary key of the strong entity will appear as a foreign key within the weak entity, but it will not be a part of that weak entity's primary key. Let's see some examples that will hopefully clarify the difference between ID-dependent and non-ID dependent relationships. In our first example, we see an ID-dependent weak entity named vehicle. We can tell that this is an ID-dependent weak entity because part of its primary key is composed of the primary key from a strong entity. In this case, the strong entity is the auto model entity, and its primary key is the combination of manufacturer and model. And in the vehicle entity, we can see that manufacturer and model are part of the primary key. This is therefore an ID-dependent weak entity. By contrast, we might use a different type of primary key for our vehicle entity, such as a VIN, or a vehicle identification number. And in that case, the primary key of the strong entity, auto model, does not appear as part of the primary key of the weak entity, vehicle. Instead, the primary key of auto model appears in the vehicle entity as a foreign key link back to the strong entity. In this case, it would be a non-ID dependent weak entity. And again, note that ID dependent relationships are shown with a solid line, while non-ID dependent relationships are shown with a dashed line. Next, I would like to talk about a different type of relationship between entities, which we can call a supertype subtype relationship. In a supertype subtype relationship, the subtype is a special case or a specific version of the supertype. As an intuitive example, consider the generic concept of a vehicle. That might be a supertype, and then we might have specific subtypes of the vehicle class such as a car or a truck or a motorcycle, where there may be unique attributes about a car or a truck or a motorcycle that we want to track, in addition to a set of attributes that we want to track for every vehicle, regardless of what specific type of vehicle it may be. This is an example of a supertype-subtype relationship. Broadly speaking, there are two different types of supertype-subtype relationships. The first is called an exclusive relationship, and the other is called an inclusive relationship. If a supertype-subtype relationship is exclusive, what that means is that each instance of the supertype can be related to, at most, one of the subtypes. So a vehicle, for example, can be a car or a truck or a motorcycle, but it cannot simultaneously be a truck and a motorcycle. That would be an exclusive supertype-subtype relationship. By contrast, we might have inclusive supertype-subtype relationships, and in an inclusive supertype-subtype relationship, the supertype can be related to one or more subtypes. As an example, consider a university, where we might have a supertype that we call person, and we might have a subtype which we call student, and another subtype which we call employee. In an inclusive supertype-subtype relationship, a given person at our university could simultaneously be a student and an employee of the university. Thus, when a supertype can be related to one or more subtypes, we call that an inclusive supertype-subtype relationship. In these supertype-subtype relationships, we will always connect supertypes to their subtypes by using the same attribute. Recall that earlier we talked about these has-a relationships. So an employee has a locker, or an employee has a parking space. In supertype-subtype relationships, if the subtype is a specific case of the supertype, then we can call that an is-a relationship. Consider our previous vehicle example. A car is a vehicle. A truck is a vehicle. A motorcycle is a vehicle. Each of those three specific subtypes has individual characteristics which make it unique, but all three can be broadly classified as vehicles, types of vehicles. These are is-a relationships. Remember that in these types of relationships, in entity relationship modeling, the subtype will inherit all of the attributes, or all of the properties of its supertype. Let's see some graphical examples which will hopefully make these concepts easy to understand. In our first example, we see a supertype-subtype relationship where the supertype is named student, and we have two different subtypes, two different types of students. They are undergraduate students and graduate students. This is an example of an exclusive supertype-subtype relationship because a student is allowed to be an undergraduate student or a graduate student, but cannot be both at the same time. Note here that we have an attribute in our supertype table named isGradStudent, for which we can imagine that values might be true or false, which tells us which of the relationship paths to follow in order to get further information about this specific student. Also note that each of the subtypes, undergraduate and graduate, contains attributes that apply only to that specific type of student. So a graduate student, for example, has an undergraduate GPA and a score on the GMAT exam, whereas undergraduate students in this model do not have those attributes. Remember that when the subtype is a specific type of the supertype, in this case a graduate student is a student, an undergraduate student is a student, then the subtype inherits all of the attributes of the supertype. Also note that we use student ID in order to link the supertype to the subtypes. In our second example, we have an inclusive supertype-subtype relationship, where our supertype is a student, and our subtypes are various student clubs. So we may have a hiking club, a sailing club. Now this is an inclusive supertype-subtype relationship because each instance of the supertype, in this case each student, can potentially be related to more than one subtype. So a student might be a member of the hiking club and the sailing club simultaneously. One last point to make on these supertype-subtype relationships. Note that we use this circular symbol with a line under it to indicate that a relationship is a supertype-subtype relationship. If an X symbol appears inside the circle, we know that is an exclusive supertype-subtype relationship, whereas if no X appears inside the circle, we know that is an inclusive supertype-subtype relationship. As our last topic for this lecture, I would like to discuss recursive relationships. If you recall earlier, we said that it's possible for an entity to be related to itself in a unary relationship. And here we want to explore this concept in a little more detail. Consider this employee entity. The primary key of the employee entity is employee ID. And we have another attribute in this entity which is named manager ID. And we see that there is a one-to-one relationship between employee ID and manager ID. In this example, the important thing to remember is that a manager ID is actually an employee ID. It's just being used with a different name here in order to allow us to map a specific type of relationship between employees. These types of recursive relationships can be very useful for tracking things like customer referrals. For example, imagine that we run a dentist's office. Each customer that we have, each patient if you will, might have been referred to us by another patient, and we might want to keep track of that information. We could track that information in our customer table or our patient table by using one of these recursive relationships. Another great use for these recursive relationships is to implement hierarchies. And that is what can be accomplished using the sort of design that we see here with our employee entity. Let's see how this works in more detail. Each of the rectangles that we see here represents a record or a row in our employee table. At the top of our hierarchy, we have employee ID number 1. And for this employee ID, the value of manager ID is null. And what this tells us is that employee ID number 1 has no manager. So we might imagine that employee ID number 1 is the CEO of the company, for example. Moving down to the next layer in the hierarchy, we have employees 2, 3, and 4. And for each of these employees, we see that their manager ID is 1. So this tells us that employees 2, 3, and 4 report to employee number 1. Or another way of saying that is employee number 1 is the manager or the boss of employees 2, 3, and 4. Further down in the hierarchy, we have employees 5 and 6. And employees 5 and 6 have a manager ID of 3. This shows us that employees 5 and 6 work for employee 3, who in turn works for employee 1. By implementing this sort of recursive relationship, I hope you can understand how we could easily track the hierarchical relationships among employees and managers for an organization that has as many levels of management as we want and as many employees as we want. We could use this approach to track employee-manager relationships for a small company containing as few as 5 or 6 employees, like the example we see here. But we could use exactly the same approach to track all of the employee and employee-manager relationships for a massive company, like a automobile manufacturer that might have 9 or 10 levels of management and tens of thousands of employees. The point to take away from this example is that we can implement a hierarchy of any arbitrary level of complexity using just this simple data modeling approach. Well, my friends, thus ends our brief exploration of data modeling and the entity relationship model. I hope you learned something interesting. Until next time, have a great day.